Hello, and welcome back to another session of high-level RISC-V programming a RISC-V emulator in a high-level language. We're writing a RISC-V emulator in C#, and last session we worked on implementing relocations, which is how we can refer to symbols in our program without having to tediously compute their offsets manually. This is a great step forward for our assembler, which will help us work or accelerate work on the emulator as well. As I reviewed the code after finishing last session, I realized that the assembler class has now become very large and it has started to sprout responsibilities that it shouldn't have. So we are going to have to do another refactoring session. And it could have been very long, so I went ahead and ahead of time made some changes and updates to the unit tests that we have that wrap our project. And then what we're going to do is, given those changes in the unit tests, we're going to retrofit them by making changes to the assembler class, breaking out functionality that should belong in separate classes. So to start this discussion, let's take a look at what that might be. So here's the project now with modifications to the assembler tests class, the emulator test class, and also the linker tests. There's a new class that contains unit tests for a non-existing class called linker. So the part where we are performing relocations inside of the assembler class really should belong in a separate class called linker. That's what linkers do. They collect fragments of executable code or assembled code or compiled code, and then they link them together and then perform relocations. So all these relocations that we've been performing in the assembler class really should be done by a separate class called linker. And also, I think I commented last session that when we're running the assembler, it generates instructions that are not relocated yet. These emitted instructions really should be collected in a class called a section. This name is used by a lot of assemblers. When you write your assembly language program, the instructions that you are emitting end up collected inside of a section, along with any symbols that might be needed and any relocations that might have been discovered. So we're going to create a new class to collect all these things, the output of the assembler, the symbols, and the relocations, along with the bytes that constitute the partially completed instructions. This section will then be fed to the linker, and the linker will create a memory from that. So we will have to change the assembler to use uh, this new destination object, so to speak. Um, we'll also break out all the error reporting that we added to the assembler. We'll place them in a separate class. And then, because, as we'll notice, the linker will contain the logic that uploads the fields. And these fields inside of the instructions is going to be the same logic that we used inside of the assembler. So we're going to take some common code in the assembler and linker and put it into its own separate class that we'll call the assembler encoder. So let's start by creating these classes, and then let's work on getting rid of all these errors in our compiler. Let's start by creating the linker, the new class linker. So the linker is a class that will take as its argument an ASM section, which is where the assembler will have dumped its output. We don't have that class yet. And it will also accept a logger, which we haven't created it yet either, and it will hang on to those things. So we'll have a section. and we'll have a logger member variable, and we'll just add them to our class like so. We will then move the relocate method from the assembler, and its private implementation method relocate as well. Yeah, scrolling is fast on this thing. All right, cut and paste. So there's our relocate method. And what we need to do here is create a memory. So this memory will be based on the section that we were given. So we will call section, and we will invent a method called 2bytes, which will be the byte contents of the section. All right, let's go now and create the ASM section class. To make it, now we need to put that in a separate file, of course. So let's do that. So the ASM section will then keep track of the symbols and relocations that we'll be generating. And so those can be stolen from the assembler class, which we already have written. So let's grab those. Here are our symbols, and here are our relocations. Let's grab those and move them over to the assembler section. And in the constructor, we will create instances. And we also need a place to store the bytes that we are emitting. And rather than having a statically allocated chunk of memory like we did before with memory, we're going to use another class called a memory stream, which you can look up. But it is the stream of bytes abstraction that we typically use for files. But this stream of bytes will actually be kept in memory. And so what we can do, or what we want to do, is write to this memory stream. Okay, and I'm going to promote this to a property. I'm going to call it memory image, and then we will promote that. Actually, for reasons that will become apparent soon, I'll just call it memory, and then have a property return. Come on. And then we'll have a property called memory image, which just returns that memory. The reason why I'm doing it this way is because we'll be copying and pasting code which is referring to the memory as memory. So it's going to be more convenient to do it that way. So then we will create the memory. The memory will take the bytes out of the uh, out of the um, out of the section. Actually, this should be happening in the linker. What am I doing? It's hard to talk and code at the same time. Yeah, so the memory stream is not actually, the memory stream will be kept in here. And this is stuff that will happen in the linker. So I apologize for that. So here in the linker, we will have a member variable, memory, and then the property memory image is what we will expose to callers. We need to implement a 2bytes method, and that is going to take the memory stream that we have and call its toArray method. That will give us an array of bytes. So what we now have is a class asm section, which has a 2 bytes method. I'm not sure why we're getting an error here. Oh, we have to return, of course. So it maintains the memory into which the assembler will be writing its output, and it will have an area where we collect any symbols and relocations that are discovered by the assembler. So the assembler will now need to start talking to the assembler section. Okay, so let's go back here. So now the assembler is complaining it doesn't have any symbols. That's fine. And no relocations. That's fine. Now the errors, this is something we're going to be putting into our logger. So let's create a new class called logger. And logger will simply just wrap that collection of um, strings, which are the error messages that we've collected so far. So we'll have a private read-only list of strings, which is the errors, and let's make that a property. So then we can make it public, and it's not read-only then. We move it here, and then we create it in our constructor. Good, so there's our logger class. Oops, so here we go. So now we need it. All right, so now all the places where we are referring to symbols, we have to actually go and redirect that to the section that that we are assembling. And the assembler now, instead of taking a memory, will now take an assembler section. So we'll change this constructor to take an assembler section, like so. Then we'll change this. We'll rename this variable to section, and then we'll take the input variable like that. And then we need to change the type. So this is now an assembler section. Good. And now it's complaining that section does not have a way to write a word, and that makes sense. We need to make that happen. So we go to the, well, actually what we'll do is we'll take the memory class and steal a copy of its write word function, and we'll put that in the asm section class. And now instead of writing to us a const or a immutable, well, it's not immutable. We have an array of bytes, but we want it to be growable. So now we have this memory object instead. So what we'll do is we'll just tell the memory object, please position yourself at the address that we want to write to, and then compute the bytes will still happen the same way it is today. And then we're going to write those individual bytes. So we'll say memory dot write byte, and we'll pass in byte 0, and then byte 1, byte 2, and byte 3. So there's our write word, and we grab the 2 overloads of write word. Now we also need write bytes, which is going to be very similar. Actually, yeah, address, and then a bunch of bytes. So what we do here is very similar. We say this dot memory position equals the address where we want to write the stuff to, and then we will ask that memory to write the bytes. Good. So now there are a lot of places where we're referring to symbols. This will need to change now to section.symbols. And the assembler, good. And then section.relocations. Now report error, that belongs in the logger. So we'll move this and put that in the logger. Make it a public method. And now whenever we try to use report error, we need to go to our logger So we need to add a logger member variable. Private logger, and then in our constructor we will hand in a logger to write to, and then we can remove this errors collection and instead hang on to the logger like that. And where is our errors collection? It's over here. Get rid of that. Get rid of that. Okay, now we're at the linker. The linker, which is going to link together a session, perform the relocations, need access to the symbols from the section. So we'll do this, and then we'll need to talk to a logger like that. All right, so these methods now, we're now calling methods from the assembler or in the assembler from the linker, and we need to move those methods out of the assembler into a new utility class that I was going to call ASM encoder. I could have called it encoder, but that conflicts with a popular .NET runtime class. So I'm just going to use a different name to avoid any annoying conflicts. So ASM encoder. And this will perform the encodings of our instructions. And now we can go to our assembler and find encode JDisplacement and move this. And that scroll is very, very fast. We'll use the keyboard. Grab that piece of code and put it over here. Let's make that a public method now. And then all the bit fields that we're going to be encoding to, or we can steal them also from the assembler. So let's go ahead and do that. They're only used in those encoding methods, so we can move them wholesale over here. Good. And then there was another one encode B displacement that also gets moved, and let's also retarget this method call. So it goes to ASM encoder, and then over an ASM encoder we put it right here, change it to public so that it's visible, format this a little nicely. All right, and then now our linker will use the same class, ASM encoder, ASM encoder. We have some syntax errors. We need a logger for the assembler. We also need a section. Instead of a memory object, we'll now create a section. And then we'll use that in our assembler. And then we no longer relocate in the assembler. We need to create a linker first. The linker takes the section that we've assembled to and the logger, and then we call relocate to do our job. And then at the end of that work, we can now extract the memory like that. Okay. Now we need to fix our unit tests because assembler doesn't expose the section as a property. That's easily done. We will just find the section and promote it to a property. So you can take a look at the section while it is being mutated. And I guess we are depending on the logger Why are we doing that? Why can't we instead create the logger and keep it as a, yeah, instead of exposing that, what we'll do, in fact, we could probably expose the section and the logger as members of this class. So let's create a setup method. Where we set up the section, and then we also set up the logger. Let's create these, and let's initialize them so that the compiler shuts up. Okay, good. So we can now remove this, and then we want the, let's see, what do we no longer need this either. We can get rid of that. And then this does what it's supposed to do. And then here now we can use our own logger to track that there were errors. Good. Okay, so Louis, Louis, I removed this in a previous test. Run. Louis only takes two operands, a destination and a source, so why bother with a second parameter then? And add UPC has the same issue. It only has two operands. Let's fix that. Assembler needs an add symbol. Okay, so let's find the assembler class and find its label method right here. So what we're going to do is we're going to break out a new method called add symbol that returns a symbol, and it takes a label and a value. And what will happen here is if the symbol already exists, we should report an error because we're trying to redefine it, but we do return the previously existing symbol. But we will have reported an error. So instead of contains key, we will then try to get the existing symbol. So try get value, and then out comes a symbol. And if that symbol did exist, then we'll just return that, but also log an error. Otherwise, the symbol is null. We create a new one then, and instead of insert pointer, we'll use value here. And then in our label method, we'll call add symbol, passing in our label and our insert pointer. There we go. And then we return the symbol that we created in add symbol. Beautiful. Finally, we have these new methods for relocation. There is a very important relocation for risk 5 that we have not implemented yet. And so I'm going to try to make as much progress as I can on that in half an hour, but I might need to do another session to finish this up because it's a rather complicated relocation. So for the time being, we'll just create a stub method here, another stub method for this one. All right, let's try building everything now and see whether all the problems have gone away. We still have two errors. Interesting. We just added these. I am not sure why Visual Studio Code does that. Let's just run all the unit tests instead. We expect one failure now. All the other methods should just work. And there's the single failures because we haven't implemented these PC-rel high and PC-rel low relocations. Good, so let's now commit our work. We will add these new files that we just created. And let's review the changes that we've made. So we created new files as an encoder, which performs the encodings. This is used both by the assembler and by the linker. And then this new class asm section, which is where we collect the output of the assembler. Then the assembler itself now has been whittled down a little bit, so all the bit fields are gone. We no longer use a memory. All the properties for symbols and relocations and errors have been moved to another class. We do expose the section though. We modified AIUPC and also LUI to no longer have two arguments. Then we have changed all the places where we refer to memory to instead refer to the section that we're currently working on. And then we use ASM encoder, removed. So yeah, all of these refactorings you watched me do, I think we're fairly satisfied that these are all correct. All our unit tests are passing as well. That gives us extra confidence. Here is another method, add symbol. So we use it in label, but you can also use it to generate symbol references to external symbols. We'll get to that maybe in a later session. Finally, we added these two new relocations, PCRL high and PCRL low. We'll get to those after we're finished this little code review. Our linker now, we just stole code from the assembler and put it in here. We haven't made any real changes. The one important thing though is that this linker can be seen as a transformation that takes an ASM section and spits out a memory image. And the memory image is ready to be executed by our RISC-V emulator. The logger, simple as can be, just a place where we store errors. The program was modified now because we have to give the assembler a section to work in and a logger to write stuff to. And then once we're done assembling, we have to first call a linker to perform the actual relocation, and only then do we get the memory. We might consider making linker.memoryImage a private entity, a private property, and then have relocate return the memory that was relocated. But let's not worry about that quite yet. Then we have our assembler tasks, which have been, well, as I mentioned earlier, updated to these new classes that we've implemented. No real sense in reviewing those. So let's go ahead and commit our work. And let's now talk about these new relocation types. So remember that in our linker, we have three relocation types already created. One for jump instructions. When a jump instruction wants to refer to a symbol, we emit a jump instruction with displacement of 0, and then the linker is responsible for patching that displacement in the instruction at a later point by handling this relocation type. So one thing that I've been glossing over is the fact that instructions on RISC-V are 32 bits long. A jump to an address, well, an address is also 32 bits long. We cannot fit the 32 bits of the displacement into the instruction itself. It wouldn't. There's just not enough room. So one quiet implicit assumption here is that the instruction address that we are encoding will fit inside of the word, and that clearly is not the case. So in a proper linker, we would have here to do some logic that would capture the case when you're trying to branch to a location that is too far away, such that the displacement from our current program counter is so long that it won't fit inside of the, in this case, 20 bits that we are afforded. So handle case when displacement is larger than 20 bits. And similarly for the B type instructions, they only have 12 bits. So we have to handle that here as well. Uh, an absolute relocation, however, that one works just fine. It's just a place in memory where we want to drop the value of a pointer or the symbol. So this relocation will not need to be changed. But, and here's one very important point, how do we get a pointer to our memory in the first place? Let's write a little scratch program to illustrate what I'm talking about. So suppose I had a program called main, like this. Simple C program. And what I'd like to do is I would like to measure the length of a string. So I want to say int L equals string length of my string Bob. And somewhere else in memory, I have an array called Bob, and it has the value Robert, like this. Now remember in C, there's actually an additional byte after the bytes for the letters in Robert, but that gets added automatically by the C compiler. In our assembler, we always have to remember that if we want to null terminate a string, we have to explicitly provide that null. But the point here is that this is a global variable, and here the Sterling call is referring to that global variable by its symbolic name. So how would we write this in RISC-V assembly language? Well, so the way we would do this would be, first of all, we would create a function, strlen maybe. So let's call that, we would say label strlen, and then we would follow up with the actual implementation of the strlen implementation. So this would loop, um, we would accept as an input parameter that is in register 10 the pointer to the string that we wish to measure the length of, and then at the end we return the value in register 10, the length of the string. So, well, we might as well implement this. It's quite trivial to do. What we start with is the only thing we have as input is register 10. And so what we want to do is keep reading from register 10 until we hit a null, a 0 byte. When we've done that, we're done. So let's write this code. We will start with a jump to a loop label called strlen head or loop, and then we'll create a label for that. And what we'll do here is we'll check to see whether, well, we'll read a byte. So we need to load an unsigned byte from the pointer that we were given, and that is a register 10, offset 0 from that, and store that in register 11. So this reads a byte from the memory that's pointed to by the value in register 10, offset by 0. And then we check to see whether that is 0, and the way to do that is to use the break if branch if not equal. So if register 11 is not equal to the contents of register 0, which is, you should know by now, is always 0, if that is the case, then we read a non-zero byte. And so now we want to jump to the body of the loop. So we'll write strlen body. Otherwise, if we did encounter a 0, then what we have now in register 11 is the location of the null pointer. But what we haven't done here is computed the actual length. So what we need to do is actually we have to remember the position where the string started. So in order to do that, we have to use some temporary variable, and I forget exactly which variable we or register we're allowed to use here, so I'm going to have to refresh my memory. Um, in this document, there should be a description of which registers to use, or we can just, yeah, we can actually use register 12, argument register 2, which is not used, and you're allowed to modify that freely. So at the entrance of this function, what we'll do is we'll copy the the contents of register 10 into register 12. And we use add I again for this purpose. We take the contents of register 10, add a 0 to that. That is then placed in register 12. So this is save value of x10 in x12. And then once our loop is done, we now have a register 11 is the value that is the end of the string. X12 will have the beginning of the string. So now we need to compute a subtraction and put the result in x10, which is the result return register for our function. So what we want to do here is do a subtraction and put the result in register 10. The subtraction is removing 12 from 11. That should give us the length of our string. And then we return to our caller by using this sequence, which is take the link register, which is register 1, add 0 to it, and then jump there and discard the current location. This is a return. So now we have strlen. That's wonderful. But now we want to call strlen from our main program. So how do we do that? Well, in our main program, which is over here, we somehow have to get the address of Bob into our register 10, which is what we use as input parameter for the strlen function. So somehow x10 gets the address of Bob. Don't know how to do this yet. And then after we've done that, then we can jump and link to strlen. And then at the end of this, when we return back, x10 will have the length Robert, which is 6. Okay. Well, the question still remains, though, how do we get the address of Bob? And the way this is done in RISC-V is by the combination of two instructions. The first instruction is the AIUPC instruction. AIUPC means add upper, I think, integer with the PC. And so what it will do is it will take the program counter, which is the address of this instruction, and then add some offset to that and put that offset in the high bits of register 10. So maybe illustrating this as an example. We have, well, the intention here is that we want to add to the program counter the difference between the location of this instruction and the location of the string Robert, which we'll put somewhere else in memory. And here I'm adding that 0 explicitly. So somehow, somehow, what we want to do is be able to tell the assembler that I want it to compute the difference between this address, which we'll have to give a label, of course. This is Bob. So I want it to compute the difference between the label Bob and the current program counter. And the way we're going to do that is by using this PC relative and then a suffix high, which says take the difference between the current position and Bob, and then keep only the high part, or high 20 bits of that, and add that to the program counter, and then put that in register 10. But then we have to fix the lower 12 bits as well. So we're going to do a add I to 10, the existing value of 10, and then the PC relative low. But here we run into a wart or a wrinkle in RISC-V. When you use this PC relative low directive to instruct the assembler to grab the low part of a symbolic reference to Bob, we don't write Bob here as we expected, as we might have expected. Instead, what we do is we give it this relocation, we tell it where the initial instruction that computed the high part is. So the AIUPC part. We need to tell the assembler this instruction here is the one that computed the relative high part. And don't ask me why this is. This is a very complicated question to answer. Suffice to say that the way we'll resolve this is by saying to the assembler, by the way, the part where we computed the high part of the relocation that we need is 4 bytes back the previous instruction. We could also call this m.label bob high and then give it the label bob high. This would amount to the same thing. In both cases, we're specifying the location of the instruction where the high part was computed. But this is a lot more typing, and we're going to be a little bit more lazy and comfortable and convenient here and just do this. So this should be fairly clear to the programmer. We're getting the address of the instruction before us, and then magic will be done by the linker to provide the correct pointer. So um, in order to implement this, and I'm running out of time, we need to implement 2 relocations, the PCRel high, which is going to be very similar to the ones we've already seen, but then the PC relative low is interesting because it will first locate the instruction where the high part is computed using this hint that says it's 4 bytes back. And then from that point, we need to discover what computation was made there. And that would be the computation of the difference between Bob and the program counter at that location. That is what we want to then store in this particular in this relocated part of the instruction of add-I. But that's a lot of work, so I'm going to end here. But please stay tuned for the next session where we finally complete this relocation type, which will enable us then to start building really large assembly language programs. Until then, I wish you safe travels. Have a good time. See you soon.